这期视频我邀请到了参与黑洞照片拍摄背后的科学家 Violette Impellizzeri。他在智利的奥马阿特卡马大型亚毫米波阵列望远镜工作了10年之久，有着丰富的射电望远镜经验。那目前他就职于荷兰莱顿大学，主要研究方向为肾长基线干涉测量及天体中的分子成分。那 Violette 将会解答一下大家对黑洞亮斑等问题的疑惑及 EHT 望远镜背后的一些知识。So here I actually prepared several questions that being asked on my video channel, and the very popular one is so why this time the image for the M87 black hole is different than the Milky Way image here, but also people more concentrate on the 3 bright spots on the paper on the image.
First of all, I find it interesting that people say it's different because the first impression when it was revealed that people were saying, oh, wow, it's very similar. But then once you get used to the similarity, you start seeing individual differences, and that's very, very fair. The reason why it's different is that even though the fundamental properties of this image are the same, namely there's a hole and there's a ring of light, so those are the same properties. There are individual differences among them. And that's due to the fact that there are 2 different sources. And so the light that we see going around, so this ring of light is given by some of whatever is happening around the black hole, some of the material, for example, the swirling around the black hole. And that's true for Sagittarius A star. And so that swirling, that inflow of material is very variable, was changing of the order of 20 minutes for Sagittarius A star. And so whatever position those were in happened to be that position when the images were taken or averaged over time. That's sort of weather around Sagittarius A star. It's like saying you take a picture of beautiful sky and you take a picture when there are clouds. Those are the clouds. They move from one image to the other, but it doesn't matter because the fundamental properties were exactly the same. So this is Sagittarius A star. And this is from one of the, it is in one of the papers. But the important thing I want to notice here is that, in fact, when you do the analysis differently, so there's a lot of analysis going on here, the position of these bright spots is slightly different. So people should not take, and these are all probabilities according to whatever model, to whatever software we used. And many softwares were employed at the same time and in parallel. And every team had to make sure that you get the same result. And that's why I say it goes down to weather. Now for M87, we don't see these clumps. Also because even though the images had the same size in the sky, M87 is in fact a much bigger ring because it's further away, it looks smaller. And so whatever happens, whatever circles around it is much slower. So we don't see so much detail. It's much further out and it was smooth. Whereas in Sagittarius A star, the ring itself is very small. It has the size of the orbit of Mercury, right? It's like around the sun. And so there you can really see stuff turning and so you see more detail as well of what's happening there.
So are you seeing that the accretion disk there is not really homogeneous?
Yes.
Okay, I see. So that's
and if we were to take, and sorry, I just reminded me. And if we were to take this image a day later, the 3 bright spots will be somewhere else.
Okay.
So that's kind of weather on top of that ring.
I saw that. So you did the observation campaign in 2017. But until right now, it's 5 years after you released the image here. So, I mean, how difficult to look over?
Yeah, it was. So the campaign was 2017, and the M87 result was published 2 years later. So it took 2 years of analysis, and then you wonder why it took another 3 years to bring out Sagittarius A star. And the reason was there were various reasons, one of them being the pandemic. So actually,
Okay.
2020 did slow down some of the collaboration because people couldn't move, couldn't travel. So it didn't stop the collaboration, but it slowed things down tremendously. And so that was part of that weight, but it wasn't the full story. Most of it was actually due to the fact that, as I was saying before, because the size and physical scale, the size of the ring of Sagittarius' star is so small, it's varying very, very, very fast. Some people said it was as an analogy, it's like taking a picture of a dog trying to bite its own tail. And the dog moves very, really fast.
Yeah.
And all the pictures will be blurred and they will all be different. And then when you average them, it just doesn't work. You have to probably shift things and make adjustments. So those adjustments took this extra time.
Okay.
And finally, and I'm going to go into a question that you may have for me later, already foreseeing that the third thing we had to take into account is not only the variability, but the fact that we're looking through the Milky Way. And so there was corrections that had to be made, scintillation corrections, because there's more material. Whereas the view to M87 is unblocked.
Yes.
Whereas the view to Sagittarius star was actually blocked by the Milky Way. So that took some extra time to handle as well.
So do you have to, come back to the Chile very often recently for the observations, or you just stay here?
For the observations of the EHT?
Yeah.
So when observing is done with EHT, which is done once per year, typically around April.
Okay. Once
May.
per year. Okay.
Once per year, it's done. It's done at the moment in a what we call campaign mode. And this is really needed because in order for most of the telescopes, in order for them to be able to observe VLBI, they have to set the telescope in a special way. So prepare it ahead of time because it's a special recording and some of the cabling needs to be changed specifically and recorders have to become. So there's a lot of pre-preparation. And so all the various sites, and it's many of them, they all work independently. And so they have to be coordinated really, really minutiously, really, really carefully.
Okay, so they have to synchronize all the data afterwards. They collect all the. Okay.
So what happens because all these telescopes are not connected, they're doing their thing, and just once per year they observe together, and the rest of the year they do their own thing. That means that the schedule that comes in has to be prepared really carefully because also you have to imagine some of these telescopes moves at different speeds. They have different requirements. So you have to accommodate. Some of them need to point more often than others, for example. Some of them don't point. Some of them move slower, like the bigger ones. Some of them move faster. And so when we make the schedule, it has to be exactly the same for all of them. They have to be always exactly synchronous on the stars. They have to take all this into account. So even making the schedule takes months. It sounds like it's an easy thing, but it takes months to actually put it together and send it and get feedback and try and test it.
What's the exposure time if you take an image for the black hole? Yeah,
so the exposure time is in this case of M87, it depends on how much source is up. Typically, usually you would observe it from the time it rises all the time, track it until it sets. So about 7 hours.
Okay.
Right, for each track, and then we average multiple tracks. For Sagittarius star, there were 4 tracks overall, but this data is only referring to one of the 4 tracks.
I wanted to ask, so what's the difference between if I use only one very large radio telescope compared to the array telescope? Multiple array telescope here. So what's the difference between those?
The biggest difference, the biggest advantage of this array is that you can de facto create a telescope that has the equivalent resolution of a telescope that's bigger. So if you want, we do make our telescopes bigger and bigger. It's not like you always want to use interferometry. There are some large single dishes. In fact, one of them in China is FAST. It's a beautiful instrument, 500 meters.
Yeah.
It's enormous. And it's a natural valley. And that sort of telescope is incredibly sensitive because you use the full 500 meters to detect these photons. And so we do make our telescopes bigger. The other one was Arecibo, it collapsed, but it was 300 meters. It collapsed recently after 30 years of beautiful science, right?
Yeah,
So it was really kind of sad and dramatic, but it worked for many years, and it also collected. Effelsberg is 100 meters, and so we do make our telescopes bigger, and that way we have more resolution, but we also have what we call sensitivity, and so every telescope has to be compromised between sensitivity and resolution. The bigger the telescope is like a bucket collecting water. The bigger the telescope, the more water this bucket can collect, literally. And so we're still interested in large dishes.
Okay.
However, at some point, unless you have a valley like the FAST, you cannot make telescope much bigger. And so what we have to do is to take them apart in order to keep the resolution. And so you create a virtual telescope that's as big as the distance, uttermost distance between them. And in the case of, for the most extreme case, which is this one to observe this black holes in the EHT, then it's a telescope equivalent to 13,000 kilometers, right? Because that's the distance between the two most telescopes, antennas, between the two antennas that are furthest. But it's not enough to put them apart. In fact, that's the reason why the EHT and submillimeter astronomy have not taken a picture before.
Okay.
It was still missing the bucket, right? Because the bucket collects the faint light. If you have something really strong, then you don't need a big bucket, then you just put these telescopes all over the world. But these telescopes are small. And so we still needed the bucket. And in this case, the bucket was provided in 2017 for the first time by ALMA, which is the biggest telescope of the whole lot. And it was brand new, or relatively new, but it was brand new also that it could join the EHT. This was done thanks to really hard work of people who made it so that ALMA is also an interferometer with an interferometer, but when it observes with the EHT, it acts as a single dish. And so the single dish has an equivalent size, is like equivalent to a size of 75 meters. And so the other telescopes are 12 meters and almost 75 to 80 meters. And so that's our big bucket. So the combination of all these telescopes scattered around the world with 13,000 kilometers and the big bucket that was ALMA, collecting all the many photons, made it so that we could take this image. Yeah. And we don't have the resolution that's better than what we have now. So 3 Schwarzschild radii is what we could observe, right?
Okay.
That's the limits of our resolving power. In order to do better than that, we would have to go in space at this point.
I mean, what do we gain when we had more telescopes into this array?
Even more telescopes. Yes. So you basically, what you do, as I mentioned previously, I refer to a telescope with many holes.
Yes. So you're actually filling the holes.
We're filling some of the holes. We're making more and more smooth because there will still be gaps between telescopes. But the trick of synthesis imaging is to sort of fill those holes as the telescope rotates. The UV plane gets filled. But if you just have a few antennas, there's still holes in that UV coverage. And so we want to fill them as much as possible. That's why we're getting more antennas. Yeah.
I know you're working at ALMA telescope. So what else besides capture the image of black hole can a radio telescope do?
Well, radio telescope like ALMA can do anything.
Okay.
I'm thoroughly enthusiastic and excited about ALMA still after 10 years. It can really do anything. We can observe other galaxies, other black holes. So not the photon ring itself or the most stable orbit, but even the gas further out. So one of the things I would say ALMA is specialized in is molecules. Okay. Observing molecules, complex and simple molecules, because that's in the submillimeter. So the region that ALMA observes in the universe is the region where most transitions, a lot of transitions reside. And so ALMA is really, really finely tuned to all of these molecules. And so around black holes, there are molecules. We observe them with water and other, HCN, HCO+. There's a lot of gas. So we can actually get dynamics, right? Because you can get not only you don't only get the orbits, but you get different maps, and you know which direction things go. You know if there's accelerations, and if there is going up, down, towards us, and Doppler shifts, etc. So there's a there's a huge richness. We can observe something that's really popular here in Leiden, as you probably know, is disk formation. Beautiful images of disks where you have a star, and now they have holes in the disk where the first planets form, and you can really catch them information.
Yeah, I saw that picture on ESO before. So
this is spectacular stuff that Alma is doing. I think it's revolutionized completely the field of disk formation, planet formation.
Internal released for the first black hole image. I mean M87 image. When was that? The first release of? I mean,
really 2019. Right?
I mean, internally released image. Yeah.
That's it's a nice question. So the first time we saw the image, so it was released in, I think, in April 2019.
Okay.
Around that time, April, May, and I think it was April. And the first time I saw it must have been the beginning of that year, the end of the previous year.
I see. Because
not that it's the first time that it was seen, but it was the collaboration was confident enough to send it around internally. Yeah.
So because I actually wondering, so if this image can released internally early enough that Stephen Hawking may able to had a chance to see the image before.
Yeah.
So
when did he pass away?
2018 March.
So it would have been a year before.
Yeah.
I think, I think at that point somebody might have seen the image already, but maybe not been confident enough, because there were sub teams that were doing this already. And as soon as the data was taken and imaged for the first time, that would have been enough to see it. I wonder what Stephen Hawking would have said about it. We'll never find out, but I'd be curious to know. Yeah.
这就是这一期视频的内容啦。如果你喜欢物理，喜欢天文，别忘了加关注。我们下期视频再见吧，拜拜。